All right, good morning. We'll get started. So today we'll finish everything up chapter 2. We'll look at chapter 2, quiz and owl, chapter 2, part 2. Next time we'll keep that. So we'll be into chapter 3 today, and we'll be checking the right spot today to get you ready for that. Okay, so let's start with number 18 here on the quiz. So determine the number of moles in 12.5 grams of carbon tetrachloride or carbon tet. So we've got 12.5 grams of CCl4. And we want 1 mole of CCl4 grams of CCl4. And we know that carbon is 12.01, chlorine is 35.45. So if we add those babies up, I think we get 118.36. And let's see, 12.5 grams. Grams are going to cancel out. We should be in good shape there, huh? All right, then we've got 23, 24, and 25. 23, 24, 25, 23. Calculate the number of carbon atoms in the empirical formula of nicotine. All right, so 23, if we assume it's 100 grams a sample, and these are the percentages, we're going to change these percents to grams, grams, grams. Step 1, get grams. We've got grams. Step 2, convert all the grams to moles. So we're going to have 74.0 grams of carbon. I'm going to line these all up. 8.7 grams of hydrogen and 17.3 grams of nitrogen. So that will get us all of our moles. I kept an extra number on that one. So I kept some extra non-sig figs, I'm going to call them. I just kept some extra numbers. It's not a bad idea to do it in this step, but okay. Converted everything to moles. Next step is to divide by the smallest, right? So we're going to divide by the smallest moles, which looks to be 1.235. So switching colors. Obviously, this is a 1. This is a 7. It looks like that's a 5, huh? Yeah. Okay, so that gets us that one figured out. 24. In 24, we have this. There's our empirical formula. We got to figure out our multiplier here, and that is our molar mass given. Divided by our empirical formula mass. In 25, we're going to line these all up. We're going to take all these percentages to grams, grams, grams. And if we line these all up, we're going to have 60.00 grams of carbon. 4.48 grams of hydrogen, 35.5 grams of oxygen. So we're going to divide by the smallest, and our smallest being 2.219. It's the top one that I'm concerned about. This is a 1, this is a 2. That top one. It's fine. So this comes out to be 2.25. this looks like a 2, and this looks like a 1. That's what you guys got, yes? Okay, so obviously we can't have C 2.25 H2O1, oops. So this is where we got to do step 4. We're going to multiply everything by 4, correct? We're going to multiply all of these by 4 to finish this problem, and then we have to add them all up. Okay, that will close the book on this quiz. You'll enter the answers like the last one. You get 1 shot. They might be in a different order. A, B, C, D might be in a different order and all that. Okay. Now, we left off on chapter 2 at the very bottom. There is, I don't know if you set this one up at all. On the very bottom of the chapter 2, this is a good problem to finish up if you haven't done it. I'm just going to lay it out, but I'm not going to finish it. This is a huge molecule, formula unit, whatever we want to call it here. All right, I'll just let you finish that. Let's go on to chapter 3. So we'll close the book on this baby. We are going to talk about chapter 3, and we are going to go to the section that lines up exactly with our lab. So let's see what we're going to do here for chapter 3. This starts out with balancing equations. But we got to talk about whether or not something dissolves in solution first. And then we're going to start putting numbers to balanced equations, which means we are doing stoichiometry. But the lab pertains to 3.4. So let's talk about 3.4. It makes sense to talk about that first anyway. So this time's out nice. So 3.4 is aqueous solutions. And aqueous solutions just means substances that dissolve in water. So an aqueous solution, NaCl, AQ, aqueous, which means it's just dissolved in water. This means dissolved in water. So what does it mean for something to dissolve? I'm going to go right to the diagram and then I'm going to come back. So here's my diagram on this page right here, and you're going to have to draw a similar type scenario for lab. This is what it means for an ionic compound to dissolve. What do we mean by an ionic compound? It starts with a metal ion. In this case, it is KCl, potassium chloride. It would not matter if it was table salt. You know, table salt dissolves. So when things dissolve, this is what happens. We know that the positive ion in the solid crystal structure. Now, this part right here, that's a solid, undissolved. You can see a salt crystal with the naked eye. You can see a sugar crystal with the naked eye. But when you sprinkle salt in water, you know it disappears. So what does it mean when it disappears? So what happens is, if it is soluble, or we say it dissolves, if water molecules can come in and overpower the attractive force between the positive and the negative ion, because this positive potassium is attracted to that negative chloride. So the question is, can water come in and surround it and shake it off enough as the molecules are moving in there and separate it? And once it separates it, it blocks it from getting back together. So now this you do not see with the naked eye as this floats around in solution. Can this potassium and this chloride hook back up again? Sure. What do? Just let the water evaporate, right? You just let the water evaporate. Then can you dissolve the salt back up again? Sure. Unfortunately, that happens on our car, correct? The liquid salt solution on the road splatters onto our car, that dries, and you see salt, visual salt again, correct? Which is going to be the shit show that's going to happen Tuesday night, Wednesday night, and Thursday, right? You know that's coming. It's ugly what's coming, seems to be, but okay. But my question is, why does it look this way? Why is this is a hydrogen, correct? Why is the hydrogen? Notice that all of the hydrogens are facing the chlorides. In here, all of the oxygens are facing the positive potassiums. And that's this. This is what you need to know. And we're going to cover this specifically in chapter 8. We know water looks like this. I'm going to put electrons down as X's. So if I write down electrons, this is hydrogen's 1 valence electron, and then oxygen, I put 6 X's in here. You see water, another way you see it is like this. Or you see it in this diagram like this. I call it Mickey Mouse. Well, it turns out, as you can see, there's a pair of electrons that make a bond. One of these electrons here is from hydrogen. The other electron's from oxygen. Likewise here, 1 electron from hydrogen, 1 electron from oxygen. Now, you can never trust an electron to do what you think it's going to do. Well, it turns out that Oxygen is more electronegative. And we have a table of electronegativities on the back side of your good periodic table here. So on the back side of your periodic table, this top right number is electronegativity. Now hydrogen is 2.20. Oxygen over here is 3.44. What that value really says is which one of those atoms wins the pull for shared electrons. The higher number is able to pull the electrons towards itself more. It's like a tug of war for those shared electrons. Which one wins? Oxygen. So what happens is this electron here is pulled towards the oxygen more. This electron here is pulled towards the oxygen more. So if the electron is pulled away from hydrogen, we know that the hydrogen is more positive. We call that a dipole coming up. Hydrogens are going to be positive, and the oxygen is going to be negative. Now, how do you make this symbol? You do an 8 with the top right missing. Now, what I want you to know, what's a summary out of all this for right now? We say that water is polar. What does that mean? It doesn't share the electrons equally, and you have positive hydrogens and you have negative oxygen. This is what makes life on this planet possible. The fact that water does this. Because pretty soon when water freezes, the oxygen from one is attracted to the hydrogen of another. And snowflakes are six-sided. And that creates that hole in the middle when water freezes. So that is why here you see when they split apart, remember now, you got positive hydrogen, positive hydrogen, positive hydrogen. And here you have negative oxygen, negative oxygen, negative oxygen, negative oxygen. I should say oxide, but. So if water has the ability to overpower the attractive force between the positive and negative ion, we say they dissolve, they dissociate into ions. And we call that an electrolyte. That is what lab is about. Do you get an ion? How do you know you're going to get an ion? How many ions do you get? So the question is, how do you know if water can split them up? Well, we have a table in the book that looks like this on page 9. So on page 9, all sodium, potassium, ammonium salts are soluble. What is that saying? Water has the ability to split the positive and negatives apart. If water can't split them apart, it's not going to dissolve. If something doesn't dissolve, you sprinkle in water, what's it going to do? You're visibly going to see the crystal just drop to the bottom and do nothing. It's not going to disappear. So there's this chart. Sodium, potassium, ammonium compounds are soluble. All nitrates, acetates, chlorates, perchlorates, salts are soluble. This is directly from, I think this was OWL or the textbook. And then you've got chlorides, bromides, iodides are soluble, except those containing lead, silver, mercury 1, which are not soluble. All sulfates are soluble, but there's always these exceptions, right? So therefore, Here's some more of the exceptions up above. On the back side of your pink sheet, here's the keys cheater chart. Look on the back side of your pink sheet, solubility table. Back side of the pink sheet, if you grid this out, it tells you it's whether or not it is soluble. I like this much better than, oh, here's the exception, here's the exception. But there's always the exception to the exception, it seems like. So if you have a grid that looks like this, you can just grid it out. So let's look at a row that is aqueous all the way across. And that aqueous all the way across should be potassiums, right? And it also should be sodium all the way across. Potassium and sodium compounds are going to dissolve in water. What are some negative ions that dissolve? That you see AQs going down, you know, acetates, bromides, nitrates. So this solubility table kind of is exact. Your lab instructor for this lab and the next lab is probably going to have you look at these rules and match them up. This is a lot of what OWL does as well. So OWL starts out, does this dissolve? And so on. And you can match it up with these rules. This continues on the back side. If you're not sure, you can always kind of look here, but try to do the rules. Look here. There's another solubility grid on the very last page that I stole from somewhere. It's kind of another similar solubility grid. So the back side also has it, the very last page. Okay, now let's talk the language so you understand the language we are talking about. So now I'm going back to page 3. When substances are dissolved in water, they undergo either a physical or chemical change that yields ions in solution. These substances constitute an important class of compounds called electrolytes. Substances that do not yield ions when dissolved are called non-electrolytes. If the physical or chemical process that generates the ions is essentially 100% efficient, all of the dissolved compound yields ions. Then the substance is known as a strong electrolyte. If only a relatively small fraction of the dissolved substance undergoes the ion producing process, it is called a weak electrolyte. Well, let's tackle that. Let's go to the next page and we're going to come back. So this is the language we use. And this is essentially what you're going to do in lab. This is the old way to do it. You actually plugged in a light bulb. If you had lots of ions in solution like salt water, this light bulb lights up bright. If you've got only a few ions in solution, it would be dimly lit. An example of that would be vinegar. And if you dissolve sugar in there, sugar will not produce any positive and negative charges. The light bulb really wouldn't light up. In lab, we actually have just a conductivity meter that's going to tell you a value on the screen. So you know if you put salt water in there, it's going to have high conductivity. It should be a high value and so on. So what do we mean by the language here? So conductivity is what you're going to measure in lab. If you get no ions, an example of that would be sugar. And the other example of that you're going to do is iron oxide. Because this iron oxide is not soluble. Now, what do we mean by that? So this sugar is going to dissolve though, right? This sugar is going to dissolve. This, you're going to see a beaker in lab of iron oxide, and it just is a gross mess. It is a solution, but basically the iron oxide is pretty much sitting on the bottom. If you get a few ions, you get a weak electrolyte. Vinegar would be an example of that. But I need you to understand what that beaker looks like. So vinegar is acetic acid. Here's my beaker. About 95% of what's in there is going to be hooked together. The other 5%, you're going to get H plus, and you're going to get C2H3O2 minus. How many ions do you get when you drop 100 of them in there? The total ions you get is 10 ions. That's another thing that's going to be talked about in lab this week. If I drop 100 vinegar molecules in water, 95% of these hydrogens stay attached. 5%, 5 out of 100 of these split up into ions. How many ions do I get? If 5 of these split up, I get 10, correct? Because it produces 2 ions. If you have a strong electrolyte, salt, everything is going to be Na pluses and Cl minuses. Everything is split up. If I dissolve 100 NaCls, how many total ions do I get? I get 200, correct? I get 200 because every time I put 100 in, I get 2 ions that split off. So we are going to talk about, that's what we're going to talk about in lab. Again, if you have an electrolyte, what do you have? A strong electrolyte, you got lots of ions in solution. If you have a weak electrolyte, you get just a few ions in solution. If you have a non-electrolyte, you don't have any ions in solution. Okay, let's go back. We still got to work on the language, this language yet. So let's summarize. If things dissolve, they can produce ions in solution. Not everything forms an ion in solution. So ionic electrolytes. The figure shows a dissolvent of KCl in water. The polar water molecules. We know now that we have plus and minus charges here, correct? Partial charges. Polar water molecules are attracted by the charges of K plus and Cl minus ions. The electrostatic attraction between an ion and a molecule with a dipole is called an ion-dipole interaction. That is the attractive force here between these. Ion-dipole interaction. Ion-dipole interaction. If water can overpower the electrostatic bond forces between the positive potassium ion and the negative chlorine ion, the ions split apart, and we say that KCl is soluble, which means KCl is going to be aqueous. What that truly looks like is this. If you have KCl solid and added water to it, this is a solid crystal of KCl, you are going to get K plus, we write aqueous, and you're going to get Cl minus, we write aqueous like that. In lab, you're going to talk about how many moles of ions you get. Be careful now, because the next thing would be something like magnesium nitrate. Magnesium nitrate is aqueous. Mg plus 2 aqueous plus 2 NO3 minus aqueous. Which one of these produces more ions in solution? If I dissolve 100 potassium chlorides, I'm going to get how many ions total? 200, correct? Or 1 dozen produces 2 dozen, or 1 mole produces 2 moles. If I have magnesium nitrate, if I dissolve 100 magnesium nitrates, how many total ions will I get? 300. Which one should have a higher conductivity? Whichever one produces the more ions. Whichever one produces the more ions. This will show a higher conductivity, it should, than this. It's all about how many ions you get. And all you have to do is look right here. Now notice the nitrates stay together. Do not split up nitrates. So you're going to get magnesium plus 2 floating around in solution and 2 nitrates. This should conduct more than this. What do we say this happens here? We call this dissociation. Dissociates into ions. All right, let's go to this page right here to help us out a little bit as well. So in aqueous solution just means water, correct? Liquid water. Let's try to give examples of these. An ionic compound starts with a metal ion. Starts with a metal ion. What's an example of that? Table salt would be an ionic compound, right? Table salt. Now, on this side, if you have molecular compounds, what do we say about molecular compounds? Non-metals. Does not start with a metal ion. These can be acids. And weak bases. So down here, strong acids, an example of this would be HCl. A weak base, NH3, or a weak acid, vinegar. So strong acids are going to produce all these ions in solution. What would you get? You would get H plus, aqueous, and Cl minus. H plus and Cl minus for that strong acid. And over here, what would you get for the salt? You would get Na plus, aqueous, and Cl minus. Strong electrolyte, 100% ions produced. 100% ions. Weak electrolyte, usually less than 5% produce ions. Less than 5% ions. And then molecular compounds like glucose. Non-electrolytes. No ions in solution. Okay, remember though, when you get 100% ions, you can still get a stronger electrolyte if it produces more ions in solution. So that's going to be the discussion in lab. All right, let's backtrack now to, well, page 1. So we'll backtrack to page 1. And we're going to take these compounds and we have to balance equations. And we know that on the left side of our arrow, now our arrow pretty much means yields or equals. We can put in what state they're in. CH4 is a gas. Oxygen is a gas. Carbon dioxide is a gas. And we actually get both here, but I'm going to put L for liquid. So we know we have reactants on the left, we have products on the right. We balance equations with coefficients. What are coefficients? Coefficients are these big numbers in front. We do not put them in the middle. They are always in front. And Al does a lot. Al starts out, I believe, with diagrams like this. We know that this is hydrogen, hydrogen, hydrogen. This is my carbon then. Oxygen, 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 oxygen. Over here, I have carbon dioxide. And I have water. So we know an equation is balanced when the same number of each atom is on both sides of the equation. I have a total of, when I put a 2 in front of here, I've got 4 oxygen atoms total. 1, 2, 3, 4. I have 2 oxygen atoms in my carbon dioxide, but I need to put a 2 in front of this, so I get 2 more oxygens. So when an equation is balanced, it's the same number of atoms on each side, and the reactant side and on the product side. So there's a specific order we should do that in, and that's this order right here. So compounds that contain polyatomic ions, this might be, does it contain nitrate? Does it contain ammonium? Metals, left of staircase line. And that staircase line is this line here. Left of the staircase, then non-metals except hydrogen and oxygen. Then you do hydrogen, then oxygen last. All right, let's do this problem. Let's write this one out quick. We'll write it out. Nitrogen. I guess I can put gas plus oxygen gas. And we get dinitrogen pentoxide. I'm hoping that's a gas. Okay, I'm looking at what you can do for quiz questions so far. And it looks like we can't do very many yet. We can do number 12, 26. It looks like 12 and 26 is all the way we started. 12 and 26. But I would be poking around in OWL. I would be poking around in OWL. So you kind of know what you're going to do for lab this week. Some of you have lab at 1 o'clock today, so that'll work.